Hi, my name is Annika Patka, and this is my Lab 2 presentation for my Physics 1 class at Georgia Tech. This lab focuses on the analysis of the motion of a falling object through Newton's second law, which states that the acceleration of an object is proportional to the change in velocity over the change in time, which is also proportional to the net force over the mass of the object. The two main forces in question are weight and drag force. Weight is a gravitational force, which is designated by mass times acceleration due to gravity. Drag force, however, is resistant to motion and is caused by movement through a fluid, which in this case is air. I've included two diagrams, one to note just the presence of gravity, which just has one arrow, and one that also notes the presence of drag force, which includes an arrow pointing upwards. Additionally, this lab questions the presence of terminal velocity, which occurs when drag force and weight are equivalent, to give a net zero force and a constant velocity. To analyze these principles experimentally, I dropped my system, a cat toy, from rest and observed its interactions with its surroundings, which in this case is the earth and air. I chose to drop a small cat toy from rest as its small mass would allow me to view its motion more easily. To the left on this slide, you can also see my diagram of the forces acting upon the cat toy. Weight acts downward, whereas drag force opposes the motion and acts upward. I've also included my data and tracker points. The tracker points show that as my cat toy falls, it falls at a faster and faster rate. This notes the presence of acceleration due to gravity and weight. Before getting into my two specific models, I wanted to include the general changes I made to be able to model this motion. All of the changes shown above are consistent across each of my glow scripts. As noted in the top right corner, I included the mass of the cat toy as well as a time step and time length that works with the original video. Additionally, I wanted to include the position and velocity update equations that I used throughout all of the models. To derive the updating position equation, I simply took the average velocity, which is equal to change in distance over change in time, and rearranged it to get the final distance is equal to the initial distance plus the average velocity times change in time. Similarly, the final velocity is equal to the initial velocity plus acceleration times time. This can be rearranged per Newton's second law to be velocity final is equal to velocity initial plus the net force over mass times time. The incorporation of the net force will be what changes our diagrams in the upcoming slides. My first model only took into account the force of weight. Weight is equal to mass times g, and in our case, g is 9.8 on Earth. I previously set g equal to 9.8 in the code, so to get my weight vector, I just multiplied g times the mass of a ball times the direction vector j hat. Like my last model, weight is included again. However, this time I also include the drag force, which is given as b multiplied by the velocity of the object squared. B is a proportionality vector which is found through trial and error, which I got to be 0.01. When I compare both models with the original tracker data, I find that the model that includes both weight and drag is far more accurate than the model that just includes weight. This tells us that weight is not the only force acting upon the cat toy and that drag is also acting upon it. When I increased the time of my models past that of my experimental video, I found that my model including drag allowed for the cat toy to reach a terminal velocity. This makes sense when looking at the definition of terminal velocity, which notes that a falling object reaches terminal velocity when it reaches a constant velocity. In order to reach this constant velocity, the net force must be zero, meaning there has to be an oppositionary force to the weight. In this case, the oppositionary force is the drag force, and we know that this is true because the model including drag levels out to reach a constant velocity. In the top photo, I incorporated a starting velocity of 4 meters per second in the y direction. Through the comparison of these two models, one without initial velocity and one with, we find that terminal velocity remains the same. However, when initial velocity is present, the terminal velocity is reached sooner. This makes sense because in order for an object to reach terminal velocity, the drag force must be equal to the weight, and the weight of the object doesn't change. This shows that the terminal velocity itself won't change, however, if an initial velocity is present, the object can reach terminal velocity sooner.